and you know what is the activity after time t. And I need to know this. And I know half-life. What is the half-life? I give it to you. You can calculate both things. You can calculate remaining fraction of initial activity by this law, half T over T half. What is T over T half? This is number of half-lives in this period, T. I ask what is the activity after T? 1 year, 2 years, 3 years, 5 years, 1 day, 100 day, a day, 100 years, whatever. This is a time. Okay. Divided by T half. This is number of half-lives in this period. Half to the power T to the power to the divided T half. This is the remaining fraction of initial activity. If you need what is the activity, remaining activity, remaining activity after T, you will multiply this half T over T half. This is the fraction multiplied by initial. And finish. So at any time, you can calculate what is the remaining activity if you multiply initial by the remaining fraction. This is the remaining fraction of this activity after time T for a source with half-life T half. If you need only remaining fraction, this is the remaining fraction. Remaining half, remaining 0.3, remaining 0.1, remaining whatever, you will have it. It's clear? It's clear. Okay. Now let's speak about very important thing. Now, assume I have a source like this. This is the source. First source. This is number 1. Let's say this is the over 6. And I have this amount. This is assume 1 gram. Assume 1 gram, which has about 2 10 to the power 21 atoms. Assume I have here this sample of over 60. I have this sample of still over 60. Number 2. This is big sample, small sample. Meaning we have here more atoms of cobalt 60, we have here less number of cobalt 60 than this. Okay, now, even if you need to put in mass, this is assumed 10 gram, this is assumed 1 gram. Okay, now, cobalt 60 is radioactive source. I ask you now, activity of sample 1. And this has another activity, sample 2. They are equal. A sample activity in sample 1 is greater or less than activity in sample 2. Same source, same material, same cobalt 60. But I have here, let's say 10 gram. Let's say here 1 gram. Or if you need, we have here more atoms than this atom. Which relation is correct? Activity of sample 1 or activity of sample 2?
Activity of sample 1 is greater.
Okay, so activity of sample 1 is greater than the activity in sample 2. Do you have another answer? I'm not saying
no. No, doctor. Depends on the initial activity, regardless of the mass. This is my opinion.
No, I'm not speaking. Now we have a new source from the manufacturer, from the factory of regular stop production plant. I bring this, assume this is 10 gram, assume this is 10 gram, this is 1 gram. New completely. Now, I ask you, do you think the activity, number of decay per second here, equal number of decay per second here? Because the activity is number of decay per second, number of atoms decay per second, and here there is also number of decay per second. The number here, number of decay per second, equals the number of decay per second here, or less or greater?
I think it will be the same, sir.
It will be the same.
Activity of A1 will be greater because it has more number of atoms.
Okay, I will explain.
It
Assume
will be
this
the
is,
same.
assume this is 10 gram. Okay, now I will explain, I will explain. Assume this is 10 gram. And assume this is 1 gram. I told you. Okay, now, this 10 gram, 1 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 gram, 1, 2, 3, 4, 5, 6, 7, 8, 1 gram, 1 gram. This is the source number 1. This is source number 1. I said 10 gram. Source number 1, 2, 3. So I divided this to 10 sources now. And I have here a source 1. Which activity is greater now?
Sir, A1 because it has more number of atoms.
Yes. This is higher activity than this one. This 10 gram, it's like 10 sources like this. So this 10 grams activity is greater, of course, than this 1 gram. Because this 10 gram really it is 10 sources like this. So the activity here, number 1, this one is greater than activity of this source, number 2. We can say now, we have here more atoms, cobalt 60 atoms, than the number of cobalt 60 here. We have here 10 times greater than this source. The number of atoms, cobalt 60 here, is greater than the number here 10 times. 10 grams, 1 gram, 10 times. This means the activity here is greater than here. And we can say activity proportional to number of atoms. This is the activity proportional to number of atoms in the source. If we have more atoms, we have more activity. More atom, more activity. Less atom, less activity. So, activity, number of decay per second depends on, you can say instead of mass, and it's right also, you can say number of atoms. We can say activity is proportional to the number of atoms of our radioactive source, which is the same as we say activity is proportional to the mass of our radioactive source. But we will not speak about mass, we will speak about number of atoms. Number of atoms of radioactive source. Okay. I can say activity instead of proportional to number of atoms, I will say activity, this is proportional. I can put equal and put here a constant, mathematical constant. I give this symbol lambda. This is mathematical constant times number of atoms. I started from activity proportional to number of atoms. More number of atoms in the radioactive source, high activity. Higher activity. And now in the step of proportional, I got activity equal. This is the decay, this is the constant, mathematical constant, multiplied by n. Because this process is decay, this process is decay. This is the decay of reductive source. Because this, the definition here, number of decay per second, I will call this decay constant. Decay constant. So this is mathematical constant, but I will call it decay constant because this is a process of decay, radioactivity, decay, how many decay per second. So this is decay constant. This decay constant, what is the unit of it? What is the unit of decay constant? This is number of atoms decay per second. From the definition, number of atoms decay per second equal. This is decay constant multiplied by what? This is what? This is number of atoms. So this must be what? What is the unit of this now? This constant must have unit of 1/second. Because here, number of atoms decay per second. Here, number of atoms must be here also second. Must be the same unit. So this lambda, what is the unit? 1/second. This lambda is a constant. 1/second. Okay. So activity equal lambda decay constant times n. Times n. If I know that how many atoms I have in sample, an exam give you this number, for example. Okay, an exam give you this number. I have a sample of radioactive source contains, let's say, 10 to the power 10 atoms. And the decay constant is, give you a number here. What is the activity? You multiply this by this, you get that activity. But before go to the problem and make some examples, let's take a look about this lambda. Okay. This is number of atoms. Number of atoms in the sample. In the sample, the radioactive source. This is the how many atoms decay per second. How many atoms, number of atoms decay per second. This is what? This is becquerel. Number of atoms decay per second. Assume 100. I calculate 100 decay per second, meaning 100 becquerel. If it assume I calculate, it is 1,000 decay per second, meaning 1,000 becquerel. So the activity here, when I calculate, this value will be in becquerel. So if an exam gives you this number of atoms, and you calculate this, this will be in becquerel, not in theory. I will have here, assume after calculation, multiply this by this, I give, assume 1 million. 1 million, in fact, 1 million decay per second, 1 million atom decay per second. Decay per second meaning becquerel. So 1 million becquerel. So if I solve this, the unit will be becquerel. The unit will be becquerel. This is the first thing. Second thing, this lambda is decay constant. I told you this was the proportional constant or mathematical constant. But because the process is decay, I say decay constant. It's a constant value. An exam must give to you this value. Okay, now, what is the physical meaning of this decay constant? Physical meaning. Now, I'm not speaking about the mathematical constant. No, I speak about what is the physical, what is the meaning of this constant. Let's take. Assume lambda, give you an exam, lambda, assume, give you an exam, lambda .0005 1/second. This is the number, an example. Assume I have number of atoms, 1 million, decay constant is this. What is the activity? So you multiply and you get activity. Okay, finish. But what is the meaning of this constant that he gives you? 0.0005, 1/second. I told you lambda, unit of lambda is 1/second. 1/second. Okay. Lambda, 0.0005. What does this mean? Physically, I will write this now in fractional form, not decimal. I will write lambda in 5/1. 2, 3, 4. 5/10,000. This is this. But this is decimal form. This is fractional form. See. Okay. 1/second. Now, the meaning now. If you have a sample, which has 10,000 atoms, your source has 10,000 atoms. Your radioactive source has 10,000 atoms. 5 will decay each second. Again, if you have radioactive source contain 10,000 atoms, this is the number of atoms. 5, only 5 of them will decay each second. This is the meaning of decay constant. This is the meaning of decay constant. 5/10,000, meaning the sample, each 10,000 atoms, 5 only from this 10,000 will decay each second. So this is 1/second. Okay.
Sir, I have one question. It means
Now,
decay constant higher.
if I know this, I can say in another way. Let's take another example. Lambda, assume lambda equals, let's say 8 10 to minus 5, 1/second. 8 multiply 10 to minus 5, 1/second. Assume I give you this constant. What is the meaning of this constant? It's a number, but the meaning of this number. Okay, I will explain. Lambda equals, let's say how much? 8 times 10 to minus 5, 1/second. What is the meaning of this number? I will write it in the fractional form to give the meaning both in fraction form. This is 8 divided 1, 2, 3, 4, 5 zeros. 1/second. If your source has 100,000 radioactive atoms, your source has 100,000 radioactive atoms, 8, only 8 will decay during 1 second. So this 100,000 try to decay, try. Only 8 succeed to decay. So each second only 8 will decay among this 100,000. This 100,000, each one try to decay, but only 8 will succeed to decay each second. This is the mean. Okay, now assume I have in my hand, basketball. And now I try to use it to the past. I tried 100 times. I tried 100 times. This is number of trial. Number of trial. I tried to make 100 times. I succeed only 20 times. 20 times I succeed. Succeed 20 times. Try 100. Succeed 20. I can say the probability of succeed is what? 20 over 100. Probability of succeed is 20 number. I succeed divided 100 trial. This is my what? Probability to succeed. Probability to succeed. So from 100 times I try. From 100 times, is it clear? 100 times I try, I succeed in 20. So my probability is 20 divided 100. It equal 0.2. This is my probability, 0.2. What is the meaning of this 0.2? Now I will 0.2 1. If I tried 1, I will succeed in 0.2. If I tried 1, I will succeed 0.2. If I tried 120, the same. The same. Try 100, succeed 20. Now, if I say this is 0.2, this is equal 0.2, 0.2 over 1. If I try 1, I will succeed 0.2. Same situation here. This is number of trials. Or the atom try during 1 second. Only succeed 8. Only succeed 8. This is the number of trials. Try to decay. Only succeed 8. This is probability. This is probability of decay. Probability of decay. So this number, assume this is the 5 10 to the power minus 6 1 over second. I can write this like this, 5 over 1 million. Or I can write by this way, 0, 0, 0, 0, 0, 5 divide 1. The same thing, same thing. Now, this is 1 million atom try, 5 succeed only to decay. Here, if 1 atom try, this is the probability to succeed. So lambda is probability of decay for what? This is a number, This is a number now. For what? Probability of decay of one atoms in 1 second, per second. So lambda in exam give you this definition. Lambda decay constant is what? It is the probability that one atom or one nucleus decay in 1 second. As I try to get through the ball, I succeed 20 times from 100. If I try 1.2, this is my probability, same thing. Try 1, this is the probability. This is the decay constant I give to you. Because this is over 1. So now, again, activity lambda n. This is the probability for one nucleus to decay. I don't have one nucleus. I have n. The source has n. So this is the probability for one nucleus. Multiplied by number of atoms I have, this is the total activity. This is the activity. Now, let's take now an example. But before example, no. Before example, we need to know something. This is the decay constant. Assume that I have one source. Let's say one source has lambda 0.005, 1 over second. And another source number 2, another source, I have lambda from it equal, let's say 0.05 only, 1 over second. So I have two radioactive sources. The first one with a lambda equal 0.005. This is the probability that one nucleus decays each second, this 0.005. And a second different radioactive source has this decay constant, 0.05. Now, which source will decay faster? Which source will decay faster? The source number 2 or the source number 1?
Number 2.
Number 2 will decay faster. Why? Because the probability is 0.05. This is the probability to decay. And here we have 0.005. This is 5 over 100. This is 5 over 1,000. Now, the first one, 5 will decay from 100. This is 5 will decay from 1,000. If I put here 1,000 like this, I will add here 0 also. So 50 will decay from 1,000 there. Only 5 will decay from 1,000 there. 1,000, 1,000. 1,000 here, only 5. 1,000 there is 50. Because 5.05 is 50 like divided 1,000. Same atoms now as you see, but we have different number of atoms here greater. 50 will decay around 1,000 in each 1 second, but here 5. So this lambda, when we have high lambda value, meaning more decay. Okay. Now, what is the relation between T half and the decay constant? Really, an exam will not give you decay constant. It will give you half-life. Assume. I tell you decay constant, assume 0.00104, 1 over second. And tell you T half of the same source, assume, the same source. T half is, assume, I say assume, this is not right, this number is not right, but assume 3 years. We need to calculate, so I was 3 years, assume 3 years. Now, when I told you that the decay constant of this source is 0.00104, 1 over second, did you get meaning now? But I say for you, the source half-life is 3 years. Now I get meaning, I catch something. Each 3 years, the activity decreased by half. So I get no feeling by this number. Each 3 years, the activity will be decayed by half. But here, if I told you lambda constant is 0.0001.5, what is this? It's probability, but fast or slow, how half-life, what? You don't get meaning directly from this number. But if I told you half-life 3 years, you get meaning. Easy to deal. So in exam, always give you T half. And in this calculation, activity equals lambda, and I need lambda. So there is a relation between T half and lambda. What is the relation between T half and lambda? T half equals ln 2 divided lambda. In calculator, if you put ln 2 in calculator, ln 2 equal 0.093 lambda. So T half is ln 2 divided lambda. In calculator, it is 0.693 this ln. Or you can say lambda equal ln 2 divided t half. Or ln 2 you can write 0.693 t half. That's it. If you give this number, you find this. So this is the relation between t half and the lambda. If an exam gives me t half and I need lambda, okay, put t half here. But take care. This must be in seconds. This must be in second because this is 1/2. Assume I told you t half equal 30 days. What is lambda? You will say lambda equal 0.693 divided 30. I will put here 30, but this is 30 days. This is 30 days. Must be 30 times 24 to become hour. Times 60 to become minute. Times 60 to become second. So this must be unit 1/2. And how to do this must be in second. If I give it to you in year, you must multiply this by 365 times. This is now days times 24 times 60 times 60. If it is in year, 365 times 24 times 6 times 60. Now it's in second. If I assume in days, 30 days, 30 times 24 times 60. This is the relation between t half and lambda. Okay. Of course, if the t half is hard, meaning what? Meaning lambda is low. If the t half here is the denominator is high, 30 years, 40 years, this will be low. If t half is small meaning decay faster, this will be high, probability will be high. So if the decay constant, if the t half is high, decay constant is low. If the t half is slow, decay constant will be high, probability of decay high. Okay. Before going to the example, let's do this exercise. I have source number 1. Number of atoms equal 1,000. And I have here source number 2. Different source, different. This is for example cesium, this is for example coal. Let's say this is coal. Number is coal 60. And this is cesium 137. So source number 1 is coal 60. Source number 2 is cesium 137. I have number of atoms here 1,000 atoms. I have here the same 1,000 atoms. Now, activity of cobalt over 60. Activity of cesium 137. This is decay, of course, was time. This decay was time. So I have here activity. Same amount of atoms. Now, what is the relation between the activity of cobalt source with 1,000 atoms and the activity of cesium source with the same atom 1,000 also, same number? Activity of cobalt 60 is equal to the activity of cesium or less or greater. I need answer.
Depends of lambda.
The half-life is half-life for cobalt 60 is more.
Cobalt 60 is more. Okay.
We have to know lambda before for both.
So activity will be less.
Okay.
So activity will be less for cobalt 60, which is having higher.
Activity equal lambda n, right or not? Right? Activity equal lambda n, right?
Yes.
Okay.
Right.
Now, what is the number of atoms? 1,000,
Same.
1,000. Same. So, the source with higher lambda is higher activity. Source with lower lambda is lower activity. Now, which one has higher lambda? Which one now has higher lambda?
Cobalt 60.
Huh?
We don't know. We need to know the half time.
We must know. You know, remember, what is the half-life of cobalt 60?
5 years.
5.5 years.
Yeah, if we have the half time, we can calculate it.
The half-life here, 30 years. Now,
Uh-huh.
which one is higher activity?
Cobalt 60.
Cobalt.
60.
Here, we have low half-life than 30, meaning lambda here is higher than lambda here. It takes long time to decay, 30 years. Here, it takes 5 years only, lower time. So, meaning the probability here is higher than the probability here. So, if I give you something like this, equal numbers, the activity depends on lambda. Remember when I told you, if we have higher half-life, lambda is what? Lower. Low. High. Or large. Or longer half-life, meaning lambda is low. Now, this is 30, meaning lambda is low. Lower than this. So lambda for cesium is lower. Lambda for cesium is lower. Inverse proportional. Inverse proportional. This is high, this is low. Now, which has higher half-life? 30. Meaning its lambda is lower than this lambda. So lambda here for cesium is low. So activity, this number is lower than this lambda. So activity for cesium is lower than activity of cobalt, or activity of cobalt, this is higher, greater than activity of cesium. Half-life. Give you also the meaning of lambda. Low half-life, lower half-life, high probability to decay. Longer half-life, lower probability to decay. Clear this point? Like what? Assume I have here 10. Same 10, same 2 10. For the same level of liquid. But here, this valve is like this. This valve is like this. Now, this you will lose with time, you will lose with time. But after, assume 5 minutes, you will lose completely. Here, after, let's say 1 hour, you need 1 hour. Why? Did you see this valve? This is now, now lambda. This is lambda. Low valve, low opening valve, you need more time to decay, to discharge. Greater lambda, what happened to him? Discharge faster. So, you need here less time to decay. Wow, this is lambda, big lambda, and you will take less time, T-half. You will take longer time because lambda is low. You need more time. So this is that decay. Depends on what? Depends on the amount here and on lambda. So activity, lambda, N. More N, more activity. More lambda, more activity. More lambda meaning lower T half. Or if this is constant, this constant depends only on lambda. Okay. Let's go to that presentation. Inshallah, to finish this. Okay, this is some examples. Let's take only one. We solved a lot of this now. Okay, after 5 half-lives, what will be the fraction of initial activity? I say fraction. And half 5 and 5 half-lives after 5 half-lives. Okay, I told you half. How many half-lives we have? So it is half to 5. This one, B. It is B. Remember, fraction of initial, half to the number of half-lives. He told you, after 5 half-lives. Okay, half to the power 5. Okay. Now, half-life of an element is 30 days. He gave you half-life now, 30 days. How much part will remain after 90 days? Okay, you say 90, this is a total. Divided 30, 90 divided 30 is 3. So in 90 days, we have 3 half-lives. So it is half to the power 3. Half to the power 3 meaning the remaining is 1 over 8. 1 over 8. So 1 over 8. C. Okay. This is the same rule that we started now. Okay, now activity. Remember when we started with activity proportional to number of n, if we have more atoms, we have more activity. And instead of proportional, we got equal and say lambda. And this is the decay constant. It is a only number, but the unit is 1 over second. Now, what is the meaning of lambda? We give here an example. It is the probability that a nucleus, 1, meaning 1, a nucleus will decay in unit time in 1 second. Really, I need from you to release this and say in 1 second. In 1 second, because our unit is second. So unit of lambda are 1 over second, or sometimes second minus 1 or per second. There is a relation between lambda and T half. This is a relation. This is the relation. Example, what is meant by lambda equal 0.00014, 1 over second or second minus 1, same way. Golden fraction, you can say 14 nucleus will decay among 100,000. If you put this value, 0.00014 divided 1, meaning this is the probability for 1 nucleus to decay. So this is the probability that 1 nucleus will decay in 1 second. In 1 second. In exam, he asking about this. So it is a probability. It is a probability for decay for 1 nucleus in 1 second. Okay. This is a problem that this came in exam. This came in exam about 1 year ago, about 3 exams before. This equation, this problem came in exam. A source of californium-252. This source of what? Neutron. Contains 10 to power 16 atoms. So number of atoms of this source is 10 to power 16. What is the activity of the source in megabecquerel? He asked it in megabecquerel and in millicurie. Okay, half-life is 2.65 years. This is the half-life. If you see in problem, in exam, activity and they give you number of atoms, there is no only one equation we will use. Activity lambda n. Activity equal lambda n. Remember, I told you lambda. How can we get? There is a relation between lambda and half-life. There is a relation, this relation. I need lambda. I have half-life, T half. I can get lambda from this equation. Now, take care. Take care. T half in years. And this must be lambda in 1/2. So we need to convert this years to seconds. Let's apply the equation. Lambda equal 0.693 over T half equal 0.693 divided all of this. This is now number of seconds in 2.65 years. 2.65 times 365 now become day. Now times 24 become hours. Times 60 become minute. Times 60 becomes seconds. All these are inside these two brackets. Some common mistake. I bought a calculator saying 0.693 divided 2.65 times. If you do something like this, it's wrong. You must put brackets here, and when we finish from this, put brackets. So this 0.693 divided this all. But if you make without brackets, you will divide 0.693 divided 2.65, and the result you multiply by 265, you multiply by, so you make a multiplication, not division. Take care about this in calculator. Put this in brackets. Okay, now, lambda equal 8.3 10 to minus 9, 1/2, or second minus 1. This is 1/2. I have now lambda. I have number of atoms. Let's multiply this lambda by number of atoms. This is the lambda, 1/2, of course, and this is the number of atoms. And this is 8.3 10 to power 7 decay per second. Decay per second. This is number of atoms decayed per second, which is becquerel. This is becquerel. This equation gives you becquerel. I need in megabecquerel. It's easy. Put mega and divide mega. Put mega and divide mega. Divide mega meaning 10 to minus 6 here. To 10 to power 6. Above it is 83. If you need to put in millicurie, remember how we can do this? Okay, we can now convert to millicurie. Let's solve this in board. Let's solve this in board. Or another problem, another one, not one. Okay. Assume I have a source with number of atoms equal 10 to the power 80 atoms. Another problem,
Sir, we cannot see the board.
I will, oh yes, I forget to, now it is not at the top only. I forget to. Assume this is the number of atoms I have in sum. And T half is, let's say, 74 days. Iridium, for example. This is iridium, 74 days. Number of atoms, 10 to the power 18 atoms. Okay. What is that activity in, let's say, megabecquerel? And in, let's say, in cube. Let's make general. I have numbers 10 to the power 18 atoms. Just I know numbers, only the equation that I will use to calculate activity is this. Activity equal lambda n. I have n. I have n. 10 to the power 18. No problem at all. Finished. I need to calculate activity. So I need lambda. I need lambda. Take care, lambda must be, again, lambda must be in 1 over second. I have half-life 24 days. I know that lambda equal 0.693 T half over T half. Now, T half is what? 74 days. I need to change this to hours.
أولها إلى second هذه دكتور.
Yes, I need to put in seconds. So this is 74 days. I need to convert to now hours, 24.
24 hours.
Yes.
Into
and-
60 into 60.
Yes, 60 minutes.
Yes.
Then 60
60 seconds. Yes.
This is now amount of seconds in 74 days. 74 times 24, 24 days, times 24 hours, times 60 seconds, a minute, times 60 seconds. This is now London. Okay, can you please calculate? Can you please calculate?
1.0.
1 point,
1.0.
1.10,
No, 1.0.
110.
Yes.
No.
Oh.
No, you made that, I told you, you made that a common mistake. You didn't put this.
Then I put
Okay,
1.08 into 10 power minus 7.
1.084 10 minus 7.
Okay, wait a moment. Okay, excuse me, I will use the calculator here with the voice. With the voice only, I don't hear you well. Okay.
But it is 1.08 into 10 power minus 7.
3 divided 7. 4 times, excuse me, 24 times 60 times 60. Now it is this is 1, 2, 3, 4, 5, 6,
7. 7 0.
It is about 10 to minus 7. About 1 over second. About 10 to minus 7. 1, 2, 3, 4, 5, 6. Okay. 10 to minus 7. 1 over second. This is the decay constant. Okay. Now, I have decay constant. I have number of atoms, activity. Ten to minus 7. You multiply by 10 to power 18. It's equal 10 to power 11. What is the unit here?
Correct.
Becquerel. This is really is decay per second, which is Becquerel. So it is 10 to power 11 Becquerel. This is number of this is 10 to power 11 atoms decay each second. So 10 to power 11, the same Becquerel. He asked it in megabecquerel. Okay, it's easy. 10 to power 11. This is Becquerel. I need to put only M and divide it by M. Take this megabecquerel alone and give this M 10 to power 11 and the M is 10 to power 6 million. I got in numbers now. Megabecquerel, which is 10 to power 5 megabecquerel. This is now the answer in megabecquerel. This is the answer in megabecquerel. Again, becquerel. I need to put M only. Beside becquerel, put M, divided M. Look, M divided M. Now, it is 10 to the power 5 megabecquerel. I need to put also N curie. Okay. What is the activity I started with? Okay, this one, 10, 11 becquerel. 10 to the power 11 becquerel. Okay, let's go. 10 to the power 11 becquerel. I need to convert it to how many curie? Okay, 10 to the power 11. This is number. Becquerel is 1 over 3.7, 10 to the power 10 curie. Okay, now this is 10 to the power 10. With 11, I have here 10 over 3.7 curie, which is about 2.7 curie. About, I don't know what is the number exactly, like 10 to the power 2.7 curie. About. So now, as you see, this is the way in exam give you half-life, give you number of atoms, asking about activity. Take care, this must be second, 1 over second, of course, it must be second to this, come 1 over second, and the activity you calculate is becquerel. If you need to convert, it's easy now to convert between becquerel, megabecquerel, curie, millicurie, whatever. Okay, let's continue. What is the time now? Okay, that's good. Okay. Another example, you have 3.64 10 to the power 20 atoms of this samarium 284 has activity 0.6 millicurie. Now this is activity in millicurie. He gives you activity and give you number of atoms. What is the half-life of this isotope? As you see in this equation, we have 3 parameters: activity, lambda, and number of atoms. He can give you 2 and ask about the third one. So he give us activity and he give us number of N. He asked about half-life. We can get it, yes, if we calculate lambda. If we calculate lambda. Now take care. Also this one example, is one problem came in exam also. This one that came in exam, previous exam. Okay. Now, he give you the activity, give you number of atoms. I can calculate lambda. Take care now about units. Activity in what? Activity in what? In becquerel? In becquerel? No, in millicurie. Can I use this activity here? I will use, but not in this form. I need to change this to become becquerel. This activity must be in becquerel. How we can convert it? Okay, let's do this. Okay, in the board. In the board. In the board. Activity is 0.6, how much? 636 millicurie. Can I use this activity as it is? No. In this loop, activity equal lambda n, this must be becquerel. This must be becquerel. But give you in millicurie. Okay, no problem. Boil 636 millicurie. Now, take this number as it is. As it is. Boil 636. Now, milli 10 to minus 3. Curie is 3 boil 7 10 to power 10. Now it is becquerel. Now this is becquerel now. Multiply this by 3.7, you will get a number, and this is 10 minus 3, 10 to be 7. So this is now becquerel. So don't use this activity directly here. You must convert it to become becquerel, as we did now. Number, milli 10 to minus 3, curie 3.7, 10 to power 10 becquerel. Now, calculate this, you have now in becquerel. As you see here, we convert it now, and this is the number in becquerel. 2.35, 10 to power 7 becquerel. I have activity in becquerel, I have number of atoms. Now, lambda equal activity divided in. Activity divided in. By calculation, 6.46, 10 to minus 14. 1 over second, or second minus 1. That's good. Now I get lambda. Now, I will use the equation T half 0.693 divided lambda. Let's do it. This will be T half in seconds. T half will be in second now. If you need to convert to years, okay, divided by 365, divided by 24, divided by 60, divided by 60, you get in years now, in years. So, you will have T half in seconds. Convert it to years by dividing this value over 365 divided 24 divided 60 divided 60, you get in now years. And this is also another example, the same example that we studied. Okay. Now the last thing before break, we studied now 3 quantities. The first is the activity, and give the definition, number of atoms decay per second. We studied the decay constant, another quantity, decay constant. It is the probability that one nucleus decay per second. It is the probability that a nucleus, one nucleus decay per second. And we get the half-life. Half-life, it is the time required for the activity to decrease by half. Now, let's take another quantity. Really, this quantity is used only for statistical calculations. There is no meaning for it. This is mean lifetime. Mean lifetime. It's an average lifetime. It's an average lifetime. Mean lifetime, we give it tau. This tau is the symbol for mean lifetime, tau. It's equal 1 over lambda. 1 over lambda, the reciprocal of decay constant. Or it is equal 1.44 T half. What is the meaning of mean life of radioactive source? I told you this is a statistical number only. Let's give an example to explain it. Assume now we are assume now 30 persons now. In this class now we are 30. Okay. Each one has in his pocket some money. Assume I have 50 riyals. You have 100. other person has 1,000, the other has 20 riyal, other has 75 riyal. So each one has its own money. Now, I will ask, what is the average money that we have as a group? Average. You will say, okay, what do you have? I have 50. You have 1,000. You have 20. Okay, make a summation now and divide it by number of us. 30 person. We are 30 person, for example. So total amount of money with us divided by number of persons. So we can say, let's say it's 17 or 70 riyal. 70 riyal. This is the average. It looks like that each one has 70 riyals. I have 70. This is average. But this is not the real. I have 50. But average, I have 70. So this is the mean lifetime. The meaning now. It looks like, it is not real. It looks like that the nucleus will stay this time and then it will decay. All the atoms will stay waiting this time and then all will decay. This is the meaning. Has no meaning. Really, it has no meaning. It's statistical only. Okay, so now let's take an example. A radionuclide has half-life of 20 days. Half-life is 20 days. Each 20 days, the activity reduced by half. By half, each 20 days. Now, calculate the mean life. Mean life is 1.44 T half. Multiply 1.44 by 20 days, it gives you 28.8 days. What does this mean, 28.8 days? It looks like that all the radionuclide, all the radionuclide exist in this source, will wait to 28.8 days and they will decay in this at this moment. After 28.8 days, still without decay, no decay. Just reach to 28.8 days, all will decay. So this is the mean life. In calculation, some statistical calculation we need. Like what? I give you an example. Now here in Saudi Arabia, for example, if I told you that the mean life for a person here in Saudi Arabia, assume 70 years. 70 years. This is the average life for a person. Meaning that this 70 years give you some indication about what? About health care, for example. Here in Saudi Arabia, there is a health care, high level of health care. So the average life of each person is 70 years. So give you meaning about the quality of health care. Assume another country has, for example, like Japan, 80 years. This gives you what? This means that each one will live 80 years and will die? No, of course, this is not the right. But this number give you about the quality of health care there. In Japan, 80 years, higher quality. Now, for example, another country, 60 years, lower quality. Another company, 40 years, bad quality for health care. So this number is not real, but give you some indications about some other parameters. So this 28.8, we used it in some other calculation remaining for the internal dose, and this completely is not our scope. So this mean life of a radionuclide, meaning it looks like all the atom will stay without decay until reach to this value and decay. If you have lower number, meaning it will decay fast. High number, long time, take long time to decay. But we used really half-life as the real indication, and decay constant also. Okay. You will ask, for example, now I need to memorize all these equations. Activity equal lambda n. Lambda equal 0.693 divided t half, or t half equal 0.693 divided lambda. And t half and mean life is 1 over lambda, or 1.44. No, you don't need to memorize anything of this. You will have a data sheet in exam, contains all constants, all data, all equations. So you don't memorize it. But when we make more practice, you will not need this data sheet or formula sheet. You will directly use it from your mind. So now, we now get activity concept, half-life concept, decay constant concept, and the concept of the mean life. As I told you, if you need to calculate the activity after period of time, we used this equation, activity that we did first. Activity at any time equal initial multiply the fraction, 0.5 t over t half. Forget this one, A naught E minus lambda t. This is another form to calculate activity. But really, this is simple, more simple than this. This is simpler than this. So we will use 0.5 t over t half. Some person like this, okay, as you like. You can say initial activity times E to the power minus lambda t. For me, I don't like this at all. I use this. It's better for me. A is the activity after time t, AT. And A naught is the activity initial. And here we have some example. Let's, inshallah, take now break for play and lunch, and return, inshallah, to take some examples like this and finish from this subject to take the new subject, interaction of radiation with matter. So now it is, let's say we will return, inshallah, at 1